QC, quality control. Two words that symbolize the difference between mere production and successful creative growth. These words signify the endless quest for excellence that supports Japan's industrial development. And no one is better able to talk about QC than Professor Hajime Karatsu.
唐津はじめです。最近日本の製品の品質が世界的に非常に優秀である。こういう評判がもっぱらであるということは皆さんよくご承知の通りです。実は先だって外国の航空会社のパイロット
In recent years, Japanese products have gained a reputation throughout the world for their superior quality. They perform well, are reliable, and are designed well. But more, they are produced at relatively low cost, top quality and reasonable price. That is the combination that has carried them into the markets of the world. How is it possible to keep quality up and still remain competitive? All too often, people associate excellent quality with high prices. They assume that beyond a certain level, quality control pushes up costs until the product is too expensive to compete. That logic misses the most important point, that production costs decline in proportion to rising product quality. This might seem contradictory, but actually it makes good sense. First, effective quality control sharply reduces the number of defective products. Fewer products are scrapped and fewer have to be remade. You begin to see a significant decrease in overall primary costs. That is one major reason why good quality products cost less to manufacture. The second reason is that whenever a large number of defectives are being produced, something is wrong. To remedy that, machinery must be repaired or readjusted, materials must be changed, and various processes must be modified. When defective products are not being turned out, no such adjustments are needed. The result is higher productivity and lower cost.
The game of golf is a good illustration of what we mean by QC. In golf, the players compete using clubs to see who can get his ball into a small hole in the least number of strokes. The score, that is, the quality of the player's performance, is determined by his swing and his choice of club and ball. Even a robot can hit a golf ball. If the target is 230 meters straight ahead, the robot will strike the ball hard enough to carry it exactly 230 meters. And it will hit with the same precision every time.
The principles of QC are well illustrated in a skillfully executed game of golf. QC got its start with an American engineer named W.A. Schuhart in 1927. At that time, the standard approach to quality control was to inspect all finished products after they were completed and simply throw out those that were defective. The harder the product was to make, the bigger the pile of defective items. Why, Schuhart asked, do so many defectives accumulate? He realized that the core issue was dispersion of product quality. If every item produced had exactly the same level of quality, they would all be exactly alike and would either all pass or all fail the final inspection. In actual production, however, the defective rate is never 0 or 100%. It always hangs somewhere in between. As this graph shows, most of the items will attain the prescribed level of quality, but some will fall slightly short. Still others will fall far short. The output as a whole looks like this. All products are manufactured to meet a specified standard. Those that fall below the standard are labeled defective. Defective products must somehow be identified and removed. The normal procedure is to inspect each item, deciding which should be discarded and which return to the production line. Even if a defective is salvageable, more time and money is needed to remodel or repair it. If it cannot be fixed, the labor and materials used are completely wasted. Schuhart's idea was to prevent dispersion of quality. Say, for example, that this is the pattern of production. All the products meet the standard and there are no defectives. This approach is what Schuhart called Statistical Quality Control, SQC, because statistics is the discipline that deals with the problem of dispersion. The next problem is how to eliminate the inconsistencies on the production line. When a certain item is made, if the materials, the processes, and the methods of assembly remain the same, and exactly the same conditions prevail throughout production, the resulting products should all be alike. In actual practice, however, the quality of the materials is often not constant. That means that the products will vary in quality too. When a variety of factors are uneven, the cumulative effect multiplies the inconsistency in the end products. By eliminating inconsistency for each factor, the number of defective products can be reduced. However, it is extremely costly to eliminate all the causes of inconsistency. The number of defectives may be reduced, but costs skyrocket, cancelling out the benefits. To cope with this problem, Schuhart introduced the concept of contribution rate. That is, by determining the relative impact each specific factor has on the final result, one can decide which ones demand priority.
Again, take the example of golf. What most affects the distance the ball travels? The ball itself, the club used to hit it, the golfer. Let's have a robot hit the ball using an ordinary club and an ordinary ball. Next, have the robot hit the same ball using a club with a harder shaft. The stroke style, angle and direction are all the same. As you can see, the ball travels the same distance, 230 meters in both cases. But what about the contribution rate of the ball? So far, the robot has been hitting a typical dimple type. Let's try this ball. It has the same size and weight and made of the same material, but it has a smooth surface. What happens when the robot hits this ball? It never travels more than 100 meters and its direction is not consistent. When we have the robot hit the dimpled ball again, we find it travels 230 meters every time. This experiment demonstrates that the ball contributes much more than the club to the distance the ball travels.
The trick is to determine the main causes of inconsistency. As Schuhart realized, inconsistency in production factors creates inconsistency in the end product. One way to identify where the significant inconsistencies lie is to make some deliberate change in the production factors and note the change in results. In the case of golf, by substituting different clubs and different balls, it was immediately apparent that the ball is the cause of disparity in distance traveled.
In examining the contribution rates of different factors, it's also helpful to change the person hitting the ball. Comparing ball and club, we found that the ball was a more significant contributing factor to disparity than the club. Now let's compare the performance of an amateur and a professional golfer using the same ball and club. Even a relatively proficient amateur swing is not nearly as effective as that of the professional. The amateur swing is somewhat awkward and uneven, while the professional strikes the ball smoothly and firmly. When you compare the professional golfer's performance with that of a robot, you find that the professional is so consistently good as to be virtually mechanical. The player, therefore, represents the most influential contributing factor in a game of golf. If we control the player, we can more or less control the score.
Along with quality control, the extensive use of industrial robots is one of the main reasons for high productivity in Japan. Effective quality control is a prerequisite for effective automation. A defective rate that is not extremely low is a clear indication that the workers do not sufficiently understand how to manufacture quality products. Automation or mechanization will only produce a rapidly growing pile of defectives. Automating a factory is extremely costly, moreover. In order to make such operations pay, the machinery ideally should be operated 24 hours a day. Even better, if the machinery can operate without human supervision, then you have the ultimate in automation. To make an unmanned factory feasible, however, the rate of defectives must be reduced to zero. That depends completely on successful total integration of quality control and automation.
無人運転やりますとね、翌朝来てみますとね、スクラップの山ができてる。これでは大変なことになります。ですから自動化ということと品質管理っていうのは完全に関係させてやらなければ成功しない。これはお分かりになったと思います。これまでお話した話の内容を一度ここでまとめてみます。
If Japanese products are known for their high quality and low cost, it is because quality control is being effectively implemented. Contrary to popular belief, the corollary of quality control is not high cost. QC actually cuts costs, permitting optimal operation of machinery. Defects arise from inconsistency in the factors that affect production: materials, processes, environmental conditions, etc. The rates at which these factors contribute to defects, the contribution rate, vary, and only when these factors are controlled is quality controlled. In golf, as we observed, quality control consists in assuring that the ball travels precisely to the point at which it is aimed. The relationship between quality control and automation is also very important. In order to successfully automate a factory, the defective rate should be reduced to near zero through the implementation of QC. Quality control, as we have seen, is fundamental to achieving low cost and high productivity. This is the key to the strong reputation of Japanese industrial products.
手をつないで初めて成功すると、こういうお話を申し上げたわけです。